Hello, this is Dr. Castor, and welcome to this brief tutorial associated with the Video Kinematics Analysis Lab. And in this tutorial, I'd like to illustrate a variety of examples actually done by prior students in the biomechanics class relative to the required elements of the video kinematics analysis, which include angle measurements, segment inclination measurements, and motion tracking through developing stick figure overlay at critical phases of the movement and tracking a key point or points throughout phases of the movement. And what I show you here are various examples, including a variety of methods, and we'll also cover some errors that can occur, especially with angle measurements if done incorrectly. Well, the first example we see here is a relatively simple one, and you'll notice that since it is a symmetrical activity, the squat, we can assume that the right and left sides of the body are doing similar things, and we can represent our stick figure, as is done here, as a simple two-dimensional image. In the examples given in the tutorial for generating stick figures, the example was for a pseudo three-dimensional stick figure, and there'll be an example like that in here again later. It's a relatively simple stick figure. The individual did not attempt to identify the head segment. That would have been a nice addition. The arm segment, maybe less so. The arms probably do not move a whole lot. So he was left with the trunk, the thigh, and the lower leg. The foot could also be identified here. There is action that happens at the ankle joint of dorsiflexion and plantar flexion, not because the foot is moving up or down, but because the tibia is moving over the top of the foot or away from the foot. Both dorsiflexion and plantar flexion do occur. So I probably would recommend, we'll use the stick figure on the left here as an example, in drawing a triangle representation of the foot, going from the ankle to the toe, toe to the heel, and heel back to the ankle. And then we see appropriate angle measurements taken with the angle measuring device lined up on the trunk segment and the thigh segment for the hip joint, and on the thigh segment and the tibia segment for the knee joint. You can use your discretion in terms of how few or how many angle measurements that you take for your individual chosen movement. You will find that for a movement that happens largely in the sagittal plane, there's a wealth of angle measurements that can accurately be taken, ensuring that your camera is positioned so that you capture the sagittal plane in the optical frame of the camera. For those of you that choose a more rotational type movement, it's sometimes difficult to find even a single frame where a joint will be in a position where both segments are in the plane of the camera. Let's go down and look at an older school example from back in the day when these analyses were done by taking a transparency or a piece of tracing paper, placing them over a video monitor of some format. Back in the days of VCRs and television screens, that's how this was done. And the positions of the body were tracked to generate the stick figure, and the angles could be then measured perhaps off of the stick figure. This example, however, illustrates some errors that can easily be made, whether taking those joint angle measurements by hand or whether taking them using the angle measuring device in Kinematics. Kinematics allows you to place that angle measuring device anywhere you want on the screen, and it simply measures the angle between the two segments of that angle measuring device. However, in this example, this was an attempt to capture an image of a bat swing, but the camera was placed in an orientation such that the shoulder angle, definitely this right elbow angle, and this hip angle, none of those angles included both segments in the optical axis of the camera. This, the right upper arm segment would be coming out of the plane of the camera towards the viewer. The lower arm segment, the forearm segment, may be in the plane of the camera. And if the individual took the angle measurement, the hip angle measurement using the trunk as a segment, that may have been adequate, but attempting to take the pelvis and the thigh segment likely is behind the plane of the camera, so going away. Those situations, whether a segment is coming out of the plane of the camera towards the viewer, towards the camera essentially, or going back into the plane of the camera, away from the camera, those are both situations where the segment is considered out of plane of the camera, and there are distortions that will occur that result in an inaccuracy in a two-dimensional angle measurement. Same thing with the shoulder measurement angle that is attempted to be taken here. This would be a left upper arm. That upper arm is coming out of the plane of the camera, and that's probably a major inaccuracy. The camera would essentially need to be someplace up overhead looking down in order to capture both the line between the shoulders, illustrating the trunk segment, and the humerus segment, the upper arm segment, in the appropriate plane. And because that humerus is likely coming out of the plane of the camera towards the viewer, even though the forearm segment of the left arm may be in the camera plane, that angle would still be inaccurate. So be wary, especially if you have a multi-dimensional activity where there's lots of rotations involved, where segments go into and out of various planes. There, you may just need to search through frame by frame the video to try to find a frame where there is the capability of taking an accurate measurement. And we'll see some examples of possibilities and inaccuracies, accurate possibilities and inaccuracies in some of our later examples as well. Nothing wrong with combining stick figures and inclination or joint angle measurements. What we see in this image is 3 individual measurements and 3 individual screenshots that were taken using Kinematics. On each one, a stick figure was generated, comprising both sides of the lower extremity was the attempt, but just the camera facing side of the upper extremity to generate the stick figure. And upon that stick figure, what was overlaid was an angle measurement. In this case, it was not a joint angle measurement, or the angle between 2 segments of the body, such as the knee joint down here, but an inclination measurement. And inclination measurements, as described in one of the previous videos, is the measurement between a single segment of the body and either vertical or horizontal. So what's necessary is either a vertical or horizontal reference, and we see here the forward lean of the trunk is representing using a horizontal reference. Something in the background was taken to identify the horizontal reference, which is used then to take the forward inclination measurement of the trunk. Oftentimes for trunk lean, a vertical measurement is appropriate, but horizontal measurement works effectively as well. And what we see in this situation, a comparison of 3 different conditions of running on flat ground, running uphill, running downhill. It's an attempt to have the position in mid-stride approximately the same in each situation. And we see the biggest difference in that forward lean comes when the individual is running downhill, much more upright. With the horizontal measurement, 90 degrees would indicate straight up, and we see a little bit of increased forward lean going uphill. That's also tends to be appropriate, and the standard approach to moving up hills basically gives more stretch into the hip joint muscles and provides a little bit more power, and it also helps with where the center of gravity is. So a little bit of increased forward lean going uphill, decreased forward lean to be more upright. Again, probably an issue of being able to keep the body center of gravity within the base of support. Another inclination measurement was taken here, if you look closely, and that's the inclination of the actual incline. The student attempted to use that inclination measurement to indicate how much uphill or downhill the individual was actually running, which was a nice touch as well. So this is an example of both an inclination measurement overlaid over the top of the stick figure representation of the body. Now there's a lot in this particular figure which illustrates the value of doing some post-image processing with your particular images that you generate. This particular example, we see a similarity to the previous one. We see a stick figure overlay. In this case, the individual was applying the pseudo three-dimensional stick figure analysis, basically attempting to track both right and left arms, or represent both right and left sides of the body in the stick figure representations. And then appropriate joint angle measurements were taken in order to make comparisons. The student, the analyzer, determined that knee joint and hip joint angle measures could be taken accurately across all phases of the movement. So in this situation, we have a comparison of initial contact, mid-step, push-off, and then that mid-swing position on the other side of the body. We see a comparison of 4 positions, but then we also see that flat ground, uphill, downhill comparison that's made. It seems like I recall the first draft of this analysis in meeting with the student, and this was 1, 2, 3, 4 times 3, 12 images, and it was 12 pages long. I suggested doing some creative cropping of the images and perhaps trying to minimally generate a 4-segment sequence illustrating those 4 critical points and phases of the analysis. And the individual actually took that one step further and made the comparison of the three inclines, uphill, downhill, and flat, all on one page. The more you can fit on one page without making things too messy, the more of the requirements that can be fit on one image without having too much overlap, so they are still clear to the viewer. That can actually allow you to make some observations and draw some conclusions that are sometimes difficult to do when you're looking at items individually. So again, what we see here are stick figures comprising the requirement of 1 per critical point across their phases, and joint angles that are overlaid across those images. One more point to add on this particular form of analysis is this person definitely used the video kinematics analysis to the extent of its applicability. There's no select requirement that you make comparisons, but there is the capability to make comparisons, in this case, of joint angles across points in phases. And this person chose to do a comparison across 3 different running types and the 3 different inclines. You will find, as mentioned in previous lab analyses, that if you do try to plan in some form of comparison, it typically makes writing the discussion and application of appropriate biomechanical concepts in that discussion a little bit easier and a little bit more straightforward. The first thing you can do in a discussion in this type of results is note where the differences are and note where the similarities are, and then that can lead to greater insight in applying biomechanical principles in that discussion analysis. Okay, moving on. Again, in these 2 examples, we will see combinations of one method for tracking a point frame by frame using the track path function within Kinovia, and select inclination measurements as well. So let's look at the track path function first. This is an example in throwing of a football where the track path function was used. Reasonably clear distinction between the contrast of the football and the contrast of the background, so that person had success with that path tracking tool. And that might tell you something that jumps out as very insightful, or it might just be an interesting path. Sometimes you have to attempt to track a point. In this case, the person was tracking the football to identify what the particular areas of interest, what it can actually tell you about that particular movement. But even if the track path of the football doesn't tell you a lot, this individual used the tracking of the football after release. We see that the line tends to fade out a little bit here, but this football is tracked probably 2 to maybe 3 frames after the point of release. What we have in that situation is the ability to measure the actual angular trajectory of the football, the flight path. That's one option for achieving an inclination measurement. Even though it's not an inclination of a segment of the body, it is an angle of something relative to either horizontal or vertical. So that the way that this football release angle was determined, and the value is relatively small. I think it's about 5 or 6 degrees. It's difficult to identify there without zooming in a little bit more. But I think it's about 5 or 6 degrees. The angle measurement tool was taken and first lined up with something the horizontal, probably the horizon back here. It's a reasonable estimate of a measurement of what is horizontal. Then the angle measurement tool was taken and moved up to the center of the football at its point of release. So the person backed off in the frames in their path track to be a few prior to the end. The horizontal leg of the angle measuring tool was left horizontal, and the other leg was left positioned along the path of the football to get a relatively accurate measurement of the trajectory of the ball at the instant of release. Now, if you chose the other method for tracking the football, that of putting a circle or a marker right on the football, you wouldn't have the exact path, but you could still achieve this measurement. In fact, you could achieve it without a path tracking distinction at all. You would just need to take the angle measurement tool, place it on the football as it appears at the instant of release, uh, advance 1 or 2 frames to get some distance between the point of release and the ball in its flight, and then at that point reposition the angle measuring tool, the leg that's designed to go along the trajectory of the ball, to that new position of the football. And then you can either back up the 1 frame to the point of release or leave at the point of trajectory. Trajectory of an object, or as we'll see in the next example, trajectory of the body, that's another way to meet the requirement of an inclination measurement. Now, we'll also notice on here that there are 2 inclination measurements. In addition to the flight path of the ball, the individual chose to examine the forward lean of the trunk. This is an example where vertical is the appropriate reference. So the angle measurement device was taken, probably lined up with something like a telephone pole in the background, or maybe lined up again with the horizontal and then moved 90 degrees so that we have a vertical indicator by one arm of the goniometer or the angle measuring device. That angle measuring device was then placed central on the spine with the other arm of that device placed along the midline of the trunk to get the forward lean. Again, it's difficult to read in the way it's printed here, but it looks like it's about maybe 15 degrees. Let's move down to a similar situation where we have frame by frame tracking using the track path function combined with segment inclinations. We also have an inclination of a trajectory. In this case, this is a long jumper, but we have a bit of a comparison. We have the long jumper at the point of takeoff with the tracked path also visible, and we have the long jumper at the point of ground contact and landing with the tracked path still visible. The approximate location of center of gravity was established here using the hip joint, or probably the mid pelvis or so, as an estimation of the center of gravity. It wasn't actually calculated, and that position was used to determine. Looks like this person left the ground at approximately 14-degree takeoff angle, and they landed at about a 21-degree incoming angle. That's appropriate since the person took off at a higher point than their center of gravity is landing at. They're basically landing further down on the trajectory, which would be the result of that difference in angles. Again, that could be something that could be applied in a discussion in the discussion section of a biomechanical concept in this case. The other inclination angle that's taken here is the inclination, or the angle that the lower leg segment makes with the ground upon takeoff. Seems like I recall in the discussion of this particular analysis lab that was a key measurement that was found in a piece of literature that the person read relative to appropriate positions of the body and technique of the long jump at takeoff. In any case, it's an appropriate angle for an inclination. It's the angle of one segment, the lower leg, with the horizontal, and there's lots of good horizontal references here. The lines on the long jump runway itself, the lines on the building in the background, the lines on the edge of the track to line those things up with. Again, a comparison which gives some interesting things to talk about in the discussion, and combinations of requirements, in this case using that trajectory path or the frame-by-frame tracking using the track path combined with segment inclination measurements. One of the first examples I saw in the biomechanics class, quite a number of years ago now, but when we did first begin using the Kinematics software in class, this was the first example that I recall where the students basically abandoned the path track tool as not extremely functional and problematic given the lighting conditions and so forth that they were trying to analyze things in, and they just decided to try using what was shown in some examples of some old school hand-drawn path tracking examples, and they just drew a circle over the bowling ball in each individual instance. Notice also we have a comparison against two bowlers here, which gives a little bit more insight into the discussion section, even though that's not necessarily required. And then they also chose another nice little feature of color coordinating the phases of movement. They just basically changed the color of the circle that they were drawing over the bowling ball during each phase of movement. And we can follow that path of the individual. They would have been taking an approach. The ball comes forward, the ball comes down, the ball goes up, and then the ball comes down into release. We see this individual releases it nice and smooth. We could also have measured an angle of trajectory here. This individual seems to loft it just a little bit. It probably comes down and bounces a little bit for the lower individual. Another thing that I've always found interesting about this particular comparison is I never realized before I saw this exact analysis that the bowling ball apparently makes a loop in space. Doesn't seem like it does that as the individual is approaching the line as the ball is taking back, but that does make sense since as the body continues to go forward, there's a portion where the ball moves back relative to the body, but the body still moves forward, and then there's a portion where the ball is accelerated and it begins to move back forward relative to the body. Whether or not that loop in space should be somewhat vertically oriented and oval like this, or somewhat more rounded like this one, whether a tight loop or whether a more gentle, broader loop is associated with appropriate technique. That'll be left up to the individual making the determinations in the analysis. But it does illustrate the value of the various features in the Video Kinematics Analysis Lab. We can sometimes see things that you cannot see in real time. We can't see this happening unless we have some kind of strobe light connection that leaves an image on our eyes as the person is bowling the ball. We can only see the image as it's occurring, essentially one frame at a time. Sometimes our eyes don't see fast enough to even see all the critical details of the movement. Try to use the various tools within your video kinematics analysis to try to identify some interesting aspects of movement that again you can see or identify that you couldn't otherwise see in direct observation of real time. It's again frame by frame tracking, but that's using a drawn object over the item that you want to track. In the video tutorial with that illustration, it's also pointed out that that does give you more information. When you see lots of overlap of the ball from one frame to the next, that's an indicator that the ball is moving at a slower velocity than when you see less overlap or distance between the ball from one frame to the next. Here's most likely one of those older school examples that the prior example was drawn from. This is an example that, again, there's two different comparisons here. This was a power clean that strength conditioning activity where a barbell is lifted from the ground and it's brought all the way up to the chest, usually with a little bit of a dip at the end, and then the performer stands up at the end to a stable position again. Two lifters were compared, lifter 1 and lifter 2, and they were evaluated. Video was captured of each lifter lifting two different weights, 175 pounds and 215 pounds. Again, even though this was taken tracking by hand off of a video screen, the same result is achieved as in the prior example in putting the drawn image right over the object to be tracked. The only real difference is that in the Kenobi example, the images are left overlaid on a single image of the actual performance. The old school method, the hand tracking method, uh, we you don't have that image, which sometimes actually gives you a little bit more latitude. It would be difficult to overlay those two bowling ball track paths one over the other or present them side by side. When we did things by hands, definitely gave one a little bit more latitude in the way they actually creatively presented things. Sometimes that side by side comparison can be useful. Again, it's not necessarily suggested that you do hand tracking. This is just given largely for another illustration of how you can conclude a lot about the performances. We can look at the upward path of the pole. They both go, this one goes slightly forward in lifter 1. Lifter 2 goes a little bit more upright, 175 pounds, a little bit more forward at 250 pounds. The biggest difference between the two is it looks like lifter 1 catches the weight much higher. The catch, that period where the weight comes to a stop at the chest, that's identified by the fact that the weight comes to an almost complete stop. We see a lot of overlay with the movements. That process tends to appear a little bit sooner for lifter 2. And also, especially with the heavier weight, lifter 2 seems to have a transition backwards in the movements. Maybe there are 215 pounds is a little bit outside of the realm of what lifter 2 would want to be using and still maintain adequate technique. Generally falling backwards with a weight either at your chest or overhead is a technique element that wants to be avoided. We even see that a little bit in the upward standing portion of the lift, the top portions with lifter 2. Again, potentially indicating some technique differences. Whether you go so far as to saying these are technique flaws, you might need to know a little bit more about the movement, but definitely could be some interesting aspects to include into the discussion. The other example given in the video tutorial for frame tracking in Kinematics was if you have a segment that you'd like to track, and the example we used was the golf club, and it's adequate to represent that with a line drawing. You can actually track multiple points with a line drawing, the beginning and ending of that line segment being two interesting parts of the movement that could be tracked. And even though this is an older school example, again, with the path tracking done by hand off of the video screen, it essentially gives you a fuller representation of the just portion of the phase that I was tracking in the previous video tutorial. And again, what we see here is the takeaway phase of the golf club. The camera was looking head on from the golfer, so looking in their frontal plane as they were set up to take the golf shot, which was the same example that was used in the tutorial on path tracking, specifically using Kinematics. This person also used some color coding, which definitely helped separate the downswing, where the club from one frame to the next is further apart because it's moving faster, from the backswing where it's closer together. We see the value of the distance between frames. We see things moving slow at the takeaway, gradually accelerates into the backswing and then slows down at the turnaround point, and then achieves massive acceleration during the downswing phase. This particular student decided that it would be a little bit messy if they tried to include the follow-through phase as well, so they jumped over and separated out the follow-through phase from the backswing and downswing phase in that analysis. Again, by having a nice well-defined point at the beginning and end of the segment, we basically see the hands tracked through a plane here, back and down, the club head tracked through a plane, back, and then down in green, and we can see differences. We see that the head of the golf club is further back during the takeaway or backswing than it is in the downswing, and that has something to do with the technique of the golf shot and the type of shot that is being hit. I know not that much about golf, but I do know that there are types of shots where the downswing wants to be very similar to the backswing, once in a while even outside of the backswing path. And then we see similar characteristics with the follow-through itself. Again, what I thought was a nice example of the third technique for path tracking. We've got using the track path with a solid line. We've got putting an object over the top of the point to be tracked, circle or marker, in this case using a line segment to essentially track 2 points, and all those can be done in Kinematics. you would just have these images with the person at some point, and the tracked paths overlaid over that actual image. Okay, let's take a look at this example. This was an analysis of the approach to a volleyball spike. So it begins on the right hand, the rightmost frame, beginning of the approach, and we see an image taken for mid-approach in the mid-frame, and the actual landing prior to the jump up in the volleyball spike in the leftmost frame. The person used the generating line segments over parts of the body with some various color coding for right and left sides to help with distinguishing parts of the body and so forth, as there is some overlap. And they are using that pseudo three-dimensional stick figure approach since the right and left sides of the body do different things asymmetrically. The other thing I wanted to point out in this movement is this is definitely a multi-plane movement. The landing, the legs are in a different plane than they are in the mid-stride or in the initiation of the movement. The arms go in and out of various planes. If I were to follow this movement up into the actual spike, we would have lots of rotations, and it's a very multi-planar activity. Were we to try to make angle measurements, let's look at the knees, for example, and I noted these issues down here as well in text. In this image in the middle, we could probably take a angle measurement using our angle measurement tool on Canovia of both the left knee and the right knee and be relatively accurate because both the thigh and the lower leg are in this two-dimensional plane that the camera is capturing. However, in the leftmost image, definitely not. That person has rotated. The thigh goes out of the frame, even though the lower leg may be in the frame of the camera. And in the right leg, probably both are a little bit out of the frame of the camera. If I were to take an angle measurement of this, I could put the angle tool on there. I could line it up with the lower leg and the thigh. It would give me a number, but that number would be inaccurate. And it would probably either be more towards 180 degrees or more towards 0 degrees than the actual true measure. I would need a camera looking at some oblique angle from out here at the side to capture those angles accurately, or a more sophisticated three-dimensional type of analysis. If we look at the initiation of the movement and those legs again, in this case, the right leg probably could be measured accurately. It looks like the thigh and the leg are pretty close to the optical plane of the camera. The other leg, not so much. This is left side facing the camera. It looks like the lower leg kind of goes behind the body a little bit. You see they're both kind of on the line here, but the hips are oriented towards us. So this one's probably the one that goes out of plane back towards the other side of the body, and the thigh probably goes that way a little bit as well. That left knee angle measurement in this case probably would have an inaccuracy, but the right knee could be measured accurately. What this person actually did was they actually measured angles at different points and a variety of actual angles. In that mid stride, this was a slightly different image than we saw up here. We see an accurate measurement of this was the left knee at impact. A person chose to take a measurement of the left hip joint up here at the instant of takeoff. Again, that's accurate. Plus it's the side facing the camera. And up here they chose to take a measurement of the what would we call that? It's basically a hyperextension angle of the shoulder joint. You might want to call that just something more general, such as the the maximum range of motion of the upper arm behind the body prior to the takeoff and the jump. They use the trunk angle. They use the total arm angle as a measurement here. That arm might be a little bit out of plane, but it's pretty close. Plus, since we're using the entire arm to draw a relatively decent conclusion about the extreme position that the arms have in that backswing of the movement, helping them initiate momentum into the jump itself. The bottom images are inclination measurements. Again, the horizontal was used as reference here. Lines on the court or horizontal, the bench in the background or the sills of the windows may be good horizontal references. And they used the segment inclination as another indicator of the extreme position. This is essentially the same image as this one up here. There may be a frame or two difference between the two, but the basically illustrates two ways to look at the extent of the hyperextension of the shoulder joint. One, the actual angle between the arm and the trunk. The other, how high up relative to the horizontal that arm actually achieved. Again, an inclination is an angle relative to horizontal or vertical. Here, the student shows the angle or the extent that the arm is above the horizontal for one measurement, and they chose a second measurement to look at the forward lean of the trunk in that initial position of the spike approach. Again, horizontal arm of the goniometer is the lower one. The upper arm of the goniometer is positioned along the body. A lot of times an inclination measurement of trunk lean is a nice complement to an actual hip joint measure. Since hip joint, when we do that practically, we have to use the trunk as the long segment to measure relative to the thigh for that hip joint. So that does give us a degree of relationship of trunk lean, but it's relative to the thigh. If we put in the actual trunk lean relative to the vertical, those two measurements combined can be insightful relative to identifying the posture of the performer at that position and time. So again, multiple things in one image. These don't need to be 5 different pages in the analysis results. Use appropriate cropping and resizing of the images. This could be presented as a single figure that has both angle measurements and inclination measurements included within it. That's the extent of the examples that I've given for you. I've tried to select a variety of approaches, a variety of movements. Again, it's up to you to identify a movement that is of interest to you. These all happen to be sports specific movements, but your select movement does by no means need to be a sport specific movement. I've had excellent video kinematic analyses done on activities of daily living, simply walking, climbing stairs, lifting objects. I've had excellent analyses done on adapted type movements such as wheelchair propulsion, crutch walking. You be the judge. Comparisons are not absolutely required since there are so many components to take advantage of. I do recommend that you think about applying the tools that you have within Canovia and within the requirements for this analysis uh, to the extent that you can apply them for your particular skill. If you have a rotational movement, for example, where it's difficult to take an angle measurement, maybe use one of the other tools a little bit more elaborately, one of the path tracking tools, for example. But again, that's up to you. And start by making sure that you meet the minimum requirements. You have an example of an appropriate number that are specified in the analysis guidelines, and maybe look at going beyond that at developing a little bit more in-depth analysis and trying to achieve a few more points and perhaps a higher grade on this particular item. It is one of the more detailed ones, so hopefully you're listening to this tutorial still with sufficient time left to complete your analysis, and that you can refer back to it, and that you can problem solve or contact me with questions along the way. Thank you very much.